Tonight's video is on section 1.3, Evaluating Limits Analytically. Your homework that we will begin tomorrow in class is out of this section 1.3, 6 through 40 even, and it is due Wednesday in class. Let's begin by reviewing what we have noticed last week. I have three graphs up here. These are all parent functions. I have a quadratic, a linear, and a cubic. On all three of these, there are no holes in the graphs, and these are not like piecewise functions where there are jumps. These are smooth, continuous functions. What we have noticed last week is when you take the limit of any of these functions as I approach any c on any one of them, it will be the same thing as inputting that value into that equation and get that y output. As an example, if c was the value of 2, the limit of x squared as x approaches 2 would be 4. Today's lesson, we will build on that. Properties of limits by substitution. The first one, the limit of k as x approaches c. So k is some constant. As an example, we'll let y equal 3, y equal k. So the limit of k, or of 3, as x approaches any c at all. As I approach any c anywhere on this horizontal line, which is just a constant, it's just k. In other words, the limit of 3 as x approaches any c is 3. Next, the limit of x as x approaches c. Well, that's the function y equals x, because again, this is the function y equals k. Made an example 3. This one here is very specific. These x's do match, so it's y equals x. Well, how do I graph y equals x? Well, the y-intercept is 0 and the slope is 1. That is y equals x. So if I choose to see the limit of x as x approaches c, so if this is 2, this would be 2. For example, if I wanted to approach 3, it would just be 3. If this was 3, this is 3, because why? Y equals k. I'm sorry, y equals x, or x equals y. They're the same output. That's how you graph this. It's up 1 over 1, up 1 over 1. So if you're at 5, the point is 5, 5. If you're at negative 4, it's negative 4, negative 4. Next, the limit of x to the n power as x approaches c. Well, let's see. Let's make an example. Y equals x squared. So that function here, and I just called that n2. Y equals x squared. In other words, that's what that function is. Y equals x squared. So let me draw that parabola. Because it could be x to the second power, x to the third power, etc. So if it was 1, it would just be 1 to that n power. Sorry, that should be at the example. C to the n power. So let me try that again. Limit of, here's your example. And let x approach 2. So what you do is you put in 2 for the function and you square it. That would be 4. Let's try another example. limit of x squared as x approaches 3. You just put in 3 for x and you square it, and that would give you 9. So if you notice, you put in c where that x is. You put 2 in where that x is. You put 3 in where that x is, and you square it, or whatever that value is. Next. Let b and n be constants. The limit of f of x as x approaches c, we're going to let it be L. The limit of a different function called g of x as x approaches that same c is going to equal capital K. So we need to know that up front before I can continue. So now I'm going to have the fourth one is scalar multiple. So for an example, the limit of b times f of x as x approaches c, well, b is just a constant, like the number 2 in front of a function. So it's the same thing, or it is equal to factor out that constant, put the 2 in front. So it's 2 times whatever this limit is, the limit of f of x as x approaches c. Well, that would be b times, well, we just said up here, let that all equal L. So this would be whatever that is. So let's do an example. The limit of 2x squared as x approaches c. We'll call the function f of x x squared, and b be the constant in front, the scalar. What I can do, because right now we have not learned any property to handle that. We've only had a property to handle this piece here. So that would be 2 times, well, we already know that. You just put in the value of c in here, c squared. Next, sum and difference. The limit of f of x plus or minus g of x as x approaches c. So the limit of the entire thing. I'm either adding 2 functions or I'm subtracting 2 functions. So that's equal to taking the limit of each one individually and adding the results or subtracting the results. So back up on top in your notes. So in fact, I can leave that here. What would that be? That would be equal to L plus or minus, that would be equal to K. That would be your answer. So let's do an example of that one. This you know how to do. So it has to be the same c value. Whoops, I already separated it. Let's put that together. X squared plus 3x. So what I can do is I can take this, as you can see, I've already separated it. So this one here, I put in 2 for x. This one here, it's just 3 times 2. So it's 4 plus 6, which equals 10. So you can see this as one function, or you can break it up into 2. And you know for a parabola, there are no holes, and it's not a piecewise function. That is just a line. So when you add that together or keep it separate, the limit is going to be by substituting it in that value of 2. It's going to be the same thing. Next, product. The limit of 2 functions being multiplied together as x approaches c is equal to the same thing as the limit of the first one times the limit of the second one. So back at the beginning, we said this was equal to L, this was equal to capital K. Let's see if I can get you an example. The limit of 2x times x squared as x approaches 1. can be written as the limit of 2x as x approaches 1 times the limit of x squared as x approaches 1. So that would be just by substitution, because that's just a line. This parabola has also no holes and no jumps. You just substitute that in. So it would be 2 times 1, which equals 2. That's the answer to that limit. Number 7, quotient. So the limit of one function divided by another function as x approaches c can be written as the limit of the numerator as x approaches c over the limit of the denominator's function as x approaches c. So let's see if we can find you an example for that one. The limit of 2x squared over 4x as x approaches 3 equals the same thing as the limit of 2x squared as x approaches 3 over the limit of 4x as x approaches 3. So that's just 2 times 3 squared over 4 times 3. That's 2 times 9, which is 18, over 12. That's 3 halves. Again, I'm allowed to use direct substitution because that's a parabola that's been vertically stretched, and that's just a line that's got a slope of 4. Both of those I can just evaluate in order to find the limit because there are no holes and there are no jumps. The last one, before we do trig, power. The limit of a function that's raised to the n power as x approaches c can also be addressed as the limit of f of x as x approaches c, all raised to the nth power. Let's try an example of that one. The limit of 2x quantity squared as x approaches 1 can be addressed as the limit of 2x as x approaches 1, and that whole output, whatever that answer is squared. So again, if I deal with the inside, I just do it by direct substitution because that's just a straight line. 2 times 1 quantity squared. The answer to that limit is 4. So now let's do a couple more examples. The limit of the quantity 4x squared plus 3 as x approaches 2. I'm going to address that as the addition of two functions. So the limit of 4x squared as x approaches 2 plus the limit of 3 as x approaches 2. This is by direct substitution because it's just a parabola. This one here is a horizontal line 3. So when I approach 2 from the right and the left, it's just going to be 3. So that's 4 times 4, that's 16, plus 3, that equals 19. Or I could see this is all one function. That's still a parabola. So let's go ahead. There's no holes and there's no jumps. So let's just substitute it in for x right here and see if I get the same output. 4 times 4 is 16 plus 3, and I do. It does not matter which way. Let's do another example. I'm going to apply the quotient property here. The limit of the numerator as x approaches 1 over the limit of the denominator as x approaches 1. That is a quadratic and that is a linear function, so therefore I can use direct substitution. Next, properties for sine and cosine. The limit of sine of x as x approaches c You just evaluate it. You just put in that value c, sine of c, whatever that answer is. Why? Because sine is a continuous function. There are no holes. And there's no jumps. Same thing with cosine. It just continues. There are no holes and there are no jumps. So the limit of cosine of x as x approaches c, you just evaluate the cosine function at c. So let's try 3 examples and then we are done with this video. The limit of cosine x as x approaches pi over 2 is just cosine of pi over 2. Go back to my unit circle. Pi over 2 is here. That's at 0, 1, and cosine, that would be 0, because every ordered pair is cosine theta, sine theta on the unit circle. Limit of secant x as x approaches pi over 2. So that can be rewritten as 1 over the limit of, let me try that again. The limit of 1 over cosine x as x approaches pi over 2. Not the entire thing, just that function. So secant x, its reciprocal function is 1 over cosine x. Now I'm going to go ahead and just substitute that in. Actually, I'm going to go ahead and divide that up with quotient. The limit of 1 as x approaches pi over 2, numerator, over the denominator. So you can see that even easier. Well, that is just a horizontal line. That's y equals 1. So the limit of that is just 1. And then this one here, you just substitute cosine of pi over 2. We already discovered that is 0, and that does not exist. You can never have a fraction with a 0 in the denominator. That does not exist. Last, tangent. We can rewrite that as sine of x over cosine of x, just this function, just like I did here, not there, as x approaches 2 pi over 3. Now I'm going to use the quotient property, the limit of sine of x as x approaches 2 pi over 3, and the limit of cosine x as x approaches 2 pi over 3. Let's see what that equals. And so we're just going to substitute that in, and I am running completely out of room. See if we can expand that paper by putting another piece underneath. So let's see, 2 pi over 3. Guess we better sketch ourselves out a small unit circle. And so 2 pi over 3 is right here. So for this ordered pair, that's in quadrant 2. And so that's a reference angle of pi over 3. So for cosine, that is, negative 1/2, and that is square root of 3 over 2. So for sine, this is sine, square root of 3 over 2. Cosine of 2 pi over 3 is negative 1/2, multiplied by the reciprocal. So that's equal to negative square root of 3. Thank you.